Okay. Well, welcome everyone to the October edition of Space Data Hackers. I'm Mike Doyle, president and co-founder of Space Northwest, a nonprofit dedicated to maximizing the impact of the Pacific Northwest on humanity's future in space. And this is our monthly meetup where we get folks together to talk about topics in space and data, deep dive on the things that we're passionate about, because when you put space and data together, you can do amazing things for the world. I see that we've got some of our participants are recent participants in NASA's International Space Apps Challenge Hackathon, which we ran here in Seattle at the beginning of the month. And we had such a great experience. Very happy to have you guys along. And super happy to have our speaker tonight. Our agenda is a talk from Ali Hamidi of Meroxa, who will be talking about ephemeris data. And that's the data that is all about where your satellite is and where it's going in space. And as you can imagine, it's a pretty important topic, super important for US Space Force. And Ali has done some pretty neat stuff helping them out and using open source tools in the process. So before I turn it over to Ali, just a couple of quick reminders. If you have not joined our meetup, please do. We're Space Data Hackers at Meetup. Sign up there and you'll get to know when we've got these events coming up. And if you're in the Seattle area, come to One Redmond's Space Summit that's happening on Thursday, November 2nd, next week. It's an event that Space Northwest is co-hosting with our friends in Redmond. It's going to be all about space and satellite innovation. Okay, so who have we got speaking with us tonight? Ali Hamidi, CTO and co-founder of Meroxa, who spent nearly 20 years in software engineering and seen a lot of how data handling has changed over that time, and spent time at Heroku and Salesforce, managing what I can't even imagine. The Kafka as a managed service. Pretty incredible. So those experiences led to Meroxa and his passion for simplifying the world of real-time streaming data. And I'm super excited to turn it over to Ali. And you should be able to share your screen once I stop.
Great. Thank you so much for having me. Super excited to be here and kind of share what we've been working on recently. So hopefully you should be able to see my screen.
Yep.
All right, cool. Yeah, so I'm going to talk a little bit about what we've done with ephemeris data for the US Space Force. It's titled From Hours to Minutes. That'll be abundantly clear. But yeah, first, here's the rough agenda of my talk. Who am I? What is Meroxa? What does the company do? The use case that I'm going to talk about, what the problem we faced was, our solution, and then I'll talk a little bit about the SP3 data format, and then I'll talk about some stats, and I'll share some resources that might be useful for anyone who wants to do data things with SP3 formatted data. So yeah, thanks, Mike, for covering that. So yeah, almost 20 years. I know in tech, 20 years is basically a lifetime. In other industries, that's probably just a drop in the bucket. But yeah, been working in and around data for a very long time. As Mike mentioned, working on at Heroku and Salesforce previously, working on very large scale deployments of Kafka, thousands of Kafka clusters or tens of thousands of customers. Even before that, I worked at a targeted advertising company. Apologies, because advertising is rough. But yeah, there I worked on a tool that analyzed over 1 billion node social graph in real time. And so yeah, I learned a lot of stuff. I've seen a lot of things. But yeah, one thing which I feel I should call out as a disclaimer, I have a lot of experience in tech. I'm very new to the space. So a lot of the stuff that I'll be discussing is from a very sort of noob perspective. So the company, Meroxa, we founded in 2020. We've raised a bunch of money from some great VCs. They've enabled us to get where we are. We're relatively small. We're about 20 people, very engineering focused, as you can imagine. And yeah, currently doing a lot of work with the US Space Force, US Air Force, and most recently signed a contract with NASA. So yeah, breaking pretty hard into the space area and learning a ton while we do it. So the specific use case I want to talk about is very focused on Ephemeris. So it's a very new space for me. And essentially, it's satellite positioning data. And so the task was to pull data from third-party providers. So these are people that put satellites in space, track data for other companies, collect all that data, stream it into the Space Force's unified data library. Essentially, that's a large database. It stores a lot of other types of data, but one core part of it is the Ephemeris data, which then powers mission systems. And so, why do we want to do this? The data is used to essentially help them avoid objects colliding into each other. And so I think based on the total numbers that we saw, they're tracking about 27,000 objects in the database right now. And so they're constantly collecting data on what's happening, and they can actually schedule maneuvers and avoid things. In particular, the case that we worked on is a provider called Spire. They provide a bunch of other data, but in particular, their satellite data was only being delivered into the UDL 3 times a day. And so necessarily, some of the data is 8 hours delayed. So that latency is pretty brutal. If you're tracking 27,000 objects and you're trying to figure out where things should be or where things should not be so that they don't crash into each other. And so for us, essentially, what we try to do is look at the tools that we have and try to come up with a solution that allows us to kind of reduce that latency down into something that's a bit more manageable, a bit more frequent, so that they can actually make decisions quickly and figure out what they need to do. And so sort of the tool chain, the tool suite that we have is a number of products. So we built Conduit. It's an open source tool. It's Apache 2 licensed. Essentially, it's a single binary. It's written in Go, so it compiles to single binary. Asterisk is there because in most cases it's single binary, but if you build your own connectors, it can actually be more. But for the most part, single binary. It's super lightweight, so it runs on very modest systems, and it's portable, so you can compile it across different architectures and run it anywhere. And so that becomes relevant if you're planning to pull data from specialized hardware. You want to run this on a plane or on some other device. You can actually compile it into different architectures and run there. And it's open source, so anyone here can go and use it for free and actually solve their data problems with it. So Conduit came about mainly from my experience at Heroku and Salesforce, where we were managing these large-scale Kafka deployments, and so experienced a fair bit of pain and suffering operating very large clusters with Kafka and Kafka Connect. And so Conduit is the result of those sort of hard-won or hard-learned lessons where we tried to address a lot of the shortcomings of Kafka and Kafka Connect. Part of the Conduit value is really the ability to run multiple connectors. And so super relevant in this case, because Spire is one provider. Space Force had 75 plus providers that they wanted to integrate with, and each provider has their own API, their own way of doing things. And so being able to spin up connectors really quickly and actually get that data flowing through the the platform was super important. And so Conduit's key value is one, having a rich pool of connectors already. And so that makes sense if you want to pull data from various databases, various SaaS products, anything like that. We already have connectors for it. But also we have a rich ecosystem and an SDK for writing your own connectors. And so again, this is particularly relevant for people here. If you have a particular data source that you want to pull data from, then you can leverage the template and the SDK to write a connector for Conduit to pull that data out and actually use it. So SpaceTrack, as an example, you could write a connector for it and actually pull data directly from the API if you have access to SpaceTrack. Another big advantage is that you can actually write a connector in any language. And so the core requirement for us is that you implement a gRPC API has to be implemented in order for the connector to actually work with Conduit. We provide SDKs in Go and in Java, and I think we have one for Python now that's publicly available. But essentially any language. So whatever your favorite language is, whatever tools that you have, especially if you work with government, often some of the tools are limited to certain languages like C# because of legacy deployments, whatever. So you can actually use those to write connectors as well. And then there's the platform itself. So this is our commercial offering. This is how Meroxa makes money. Essentially, we take Conduit. You can think of it as Conduit++. We take Conduit as a core component, and then we run it for you. We allow you to deploy custom connectors, and then we add a bunch of stream processing stuff on top of it. So you can actually pull the data in, transform it any way you want. And then we add a bunch of enterprise features on top of it as well. So you can do user management and single sign-on and a bunch of other useful enterprisey things. But really what I want to talk about today is what we actually did for Space Force and why does it work better than what was previously there. So ultimately, this is what we ended up deploying, and this is the general architecture for our solution. And so on the left side, the Spire's infrastructure. So they have some system that's connected to their ground stations that's receiving ephemeris data from actual satellites. So this is sort of being beamed down from space into their infrastructure. It's being pushed into an S3 bucket on our side. And then that's when our sort of conduit-based infrastructure picks it up and kind of continues it downstream. Essentially, we have an S3 connector. It's constantly polling the S3 bucket. It's watching for changes. So the second a new file appears in S3, it picks it up. It parses and transforms the SP3 formatted files in real time. And then it publishes it into the UDL, which is the Unified Data Library. And so the end-to-end latency across our infrastructure is typically less than a second. And it can be even less if you tune it. But in this case, just physics alone, the time it takes from the actual satellite to the ground station, and then from the ground station through Spire's infrastructure to us, that's significantly more than a second. But across our infrastructure, it's about a second. And so that's what we had initially. So this solved their problem. We deployed the platform, and this is what we got up and running. But naturally, once you solve one problem, then you can start solving a bunch of other problems. And so this is what our final implementation looks like. There's a bunch of stuff in there. I'm happy to discuss more in details later. But essentially, the core part of the platform is there. It's very good at pulling data from wherever it might be, transforming it in real time, and then pushing it to where it needs to go. In this case, the UDL was kind of the core requirement, but actually they wrote it to a bunch of other things, like data lakes and the Air Force data fabric as an example. So I do want to spend some time talking about the SP3C format. And as I mentioned at the top of the call, I'm definitely a noob when it comes to space data, space related things. So I have tons of data experience, but zero space data experience. And so the SP3 format formally is the extended standard product 3 orbit format. But the core sort of part of it is that really it contains two things: the position, which is precisely the position in 3D space at the timestamp, and then the vector, which is where I'm headed, essentially. And so those two things will allow you to apply a model and calculate it, as in at t0, it's here right now. I can work out where it's going to be in 5 minutes, 10 minutes, an hour, further on. Obviously, the further you kind of predict, the less accurate it becomes. And so that's where the value comes in. Previously, if you were only getting 3 updates a day, then you can only be like super accurate if you just got the update. And then as you drift further from the last timestamp that you received, your accuracy kind of degrades and you're going more into the it's probably here as opposed to it's definitely here. And so, yeah, working with that format was very interesting. As somebody who's worked with many data formats, this is kind of a unique prospect. So I'm going to dig a little bit deeper into the format and what it contains and what it looks like. And so here's an example of SP3 formatted file. And so it's got a bunch of boilerplate sort of header stuff that kind of describes the contents. But the meat of it, the interesting part, is really this part. And so here you can kind of see some things that stand out pretty immediately. The first part is easily recognizable as a timestamp. So that's cool. We can look at that. Timestamps are pretty easy to understand. Although working with time, and anybody who's done any amount of software engineering for any amount of time knows that time itself is like the worst aspect. A colleague of mine described it as the USB of software engineering. So you always get it wrong the first time, and then you try again, and it's still wrong, and then you go back to what you did the first time, and you're actually right. So yeah, time is hard. In this case, it's recognizable as a timestamp, but it's not really a standard format for many of the tools that we have. And so, I wrote this tool in Go. There's no built-in format for this, so you have to write a custom format and parse it out. So not too bad. Next line is the position, so indicated by the P. And so 143 is the module number. So it kind of indicates the ID of the object. And then you get X, Y, Z values, and those are positions. Totally makes sense. Interestingly, it's measured in kilometers, precise to 1 millimeter, which is cool. As someone who grew up in the UK, totally fine with kilometers, millimeters, makes perfect sense to me. The last value is a bit of a weird one. It's the estimated receiver clock error from true GPS time in microseconds. As someone who's not super familiar with space things, that doesn't really mean a lot to me. I just know that it's some fairly precise value that I need to kind of deal with, and I'll just pass it on downstream. So positions make sense, easy to parse, easy to understand. Next line is vector. And so again, you get the XYZ vector values. And so those are the changes where it's headed. Oddly, it's measured in decimeters per second, which is kind of weird. Not sure why it's decimeters and not millimeters or anything else, but that's what it is. And then the last value, which is the 999,999.9999999, is the clock rate of change. In all cases for the Spire data points, they're actually not used at all. And so typically, if it's the precise value that's provided, it's just 999,999. You can ignore it. So that's easy enough. And so, yeah, we built a parser. I have open sourced it, and I have linked it here. So if you go to this bit.ly link, you'll actually see the parser. It is written in Go, so hopefully you like Go. You're happy to work in Go. I can actually show you what it looks like. Can everyone still see my screen?
Yes.
Yeah. So here it is. This is the SP3C parser in Go. I'm not going to go through all the code. It's probably not super fun to stare at lines of code, but essentially it does what you'd expect. It takes the file, it breaks it up into the individual, pulls the satellite names, it splits the entries. It does all the things that you'd expect it to do. And then it returns a formatted record in this format, which includes the satellite name and the entries, and each entry is a timestamp, a position, and the velocity. And it's a Go file that you can just pull into your package, pull in as a package, and just use it in your application. Some stats. So yeah, we deployed this earlier in the year. And so we're processing about 10 million entries a day. And so far we've delivered well over 1.5 billion entries. So those are updates that have gone, from the actual object in space all the way through the Spire infrastructure, through our infrastructure into the UDL. It's roughly 120 gigabytes of text files, which is pretty massive for just pure text files. And yeah, I mentioned the end-to-end latency. So across our infrastructure, it's typically less than a second. But we see that, from the actual object all the way through to the UDL, it's approximately 5 minutes, we think, which is, a pretty big improvement over the 8 hours latency. And then I have some resources. So I'll share the slides, and these are clickable links. But essentially, it links to the Conduit website, which is the open source tool that we wrote. I link to the GitHub repo and the docs, as well as the connector SDK and the SP3 parser. And so if anybody is interested in doing any work with Conduit, to pull in data and actually do that transformation, stream it wherever they need it to go, they can easily do that with Conduit. And yeah, the SP3 parser code is available. The Conduit team at Meroxa is very willing and motivated to help anybody who's interested in doing anything with Conduit. You can jump into our Discord, and we'll be happy to get you up to speed and answer any questions that you have. Some additional links on the product and how it works, if anyone's interested. And yeah, that's pretty much it for my presentation. Happy to answer any questions if there are any.
Cool. Thanks so much, Ali.
Thank you.
I've got some questions, but I'll let others go first. Stan.
Thanks, Ali. Can you tell me a little bit more about the contract you had? Was it with Space Force or was it with Spire? And maybe start there. Just understand a little bit about how you got that and why just the one company? Why just Spire?
Sure. So our contract was with Space Force, with BCCD. So specifically, it's with them. The initiative was really to pull in multiple data sources. I only highlighted Spire, but actually we're working with probably 60 or more different data sources, some of which are satellite providers, but also other data sources. So we're pulling in data from pretty much anything. But yeah, most relevant for this group, it was the Spire one. We are also in talks with the other big satellite providers to pull in their data too.
So, but I thought all of this data was already getting into UDL somehow, wasn't it? Like what was happened before you came along? How was this getting into UDL in the first place?
Yeah, it's interesting. So some of the providers were pushing their data directly. Some people were pushing their data into SpaceTrack and had special licensing to get that data into UDL. I think in general, if you have a license to push data into SpaceTrack, that doesn't include the UDL, so that has to be a separate path. And so this initiative is really to kind of invert the relationship and put the burden on us or partners like us to do the heavy lifting. So in the case of Spire, who have been super amazing with us, essentially we do all the heavy lifting. They kind of exposed the APIs, told us what the data format was, and we did all the work to bridge it into the UDL essentially.
Do you know, you may not know this, but what about data that comes from not operators, but from space domain awareness sensors, maybe telescopes on the ground or in space that are collecting data? Maybe an exoanalytic telescope gets an image of the Spire satellite, then that data goes in. Do you have any idea how that gets coordinated with the actual ephemeris data from the satellite itself? Or are they just different timestamps on the same object, or do you know?
I don't know the details on how they're correlated. I do know that the UDL itself is designed to enable these types of things and basically allow cross querying across different types of data sets as well. And so I think that's what it enables. Essentially, if you aggregate all the data into one place and have this really fast way to query them, then hopefully, you'd imagine that you'd be able to do those correlations.
Now, one quick last question. What's the relationship between SpaceTrack and UDL? Is SpaceTrack a user, is UDL the core database and SpaceTrack is a user of that, or vice versa, or how does that work?
I believe they're entirely independent. They're not connected in any way, as far as I know.
Really?
Can you say a little bit more about what SpaceTrack is?
I've only used SpaceTrack as a consumer and trying to kind of explore the data. As far as I understand it, it's a sort of almost like a community powered way of tracking Ephemeris data. And you can get an account on SpaceTrack and actually query the values and look at historical data for Ephemeris. But as far as I know, it's not. I don't think it's like a commercial offering because you can sign up and poke around.
Yeah, I think SAIC might, or someone built it for, I don't know if it was Space Force or whoever. Do you happen to know when the Space Force turns this over to the Department of Commerce? Will all of this work you've done in the UDL and this stuff go with that, or is that just too far out in the future to know how that works?
I don't know how that works. I know that specifically our contract is with Space Force directly, and we have a multi-year contract. So I think we do bridge more than just Ephemeris data, and it does cover even some classified stuff. So I don't know if it'll ever really
okay,
swap hands at some point.
Got it. Okay, thank you. That was great.
Thanks.
So any other burning questions right away? Okay, I'm gonna go.
Okay.
So you're talking about files.
Yes.
Tell me a little bit about that process of the generation of the file. Is it one satellite produces one file in one pass, or
Yeah.
are there multiple satellites all writing to the same file? How does that work?
Yeah. So in the case of Spire, it's slightly different for each provider. And some providers don't even use the SP3 format. They use something proprietary or other things. In the case of Spire, the way it works is each satellite will write a file. And typically they'll bundle about 5 minutes worth of entries into that one file and then write it into our S3 bucket. And that's what we're kind of scooping up. And so for each satellite, there will be one file.
Okay, so the files themselves are relatively small, but in aggregate, they end up huge.
Some of them are pretty big, actually, because the entries are a second apart. And so there's quite a few entries in each file. So some of them will range 4 or 5 megabytes, which is, for text, it's pretty significant.
Cool. And the other question I had was, why Go?
Yeah, that's a good question. So it really came out of a lot of the experience that I had in previous jobs, just having something that's very flexible, very lightweight, very resource efficient. And so it really comes from the experience at Heroku, Heroku Salesforce, where we built a managed platform. And so Kafka and Kafka Connect is written in Java, and so it runs on the JVM. And what you find as if you run a managed service is that essentially you have this long tail where you have a very small number of customers have a very small number of connectors doing a huge amount of traffic, but you have a large number of customers with a very large number of connectors doing very little traffic. And that is basically the pathological worst case scenario for a managed service running on the JVM. It's just costing you tons to do that. And so we thought, all right, let's try to do something a little bit more efficient. And so just to give you an order of magnitude, running the database connector on Kafka Connect, the JDBC one, on average consumes about 1 gigabyte of RAM. With the Go-based conduit connector, it's about 8 megabytes of RAM. And so you're kind of seeing this massive, magnitude difference in resource usage. The other advantage is cross compilation. And so we recently had a project with the Air Force where we actually built a version of Conduit that they ran on the plane, so that they can collect telemetry data. And so it's running on specialized hardware that's ARM-based. And so you're compiling it into this ARM thing. So yeah, having something super lightweight, super resource efficient that you can cross-compile makes a lot of sense for these use cases.
Cool. Other questions? June, Matt? All right, I got another one. So, what would you consider Meroxa's competitors? What's the landscape like out there?
Yeah, it's pretty full. There's a ton of companies doing a lot of things around ETL or ELT. So if you look at Fivetran as the sort of 800-pound gorilla in ELT, and then you get some specialized tools like Ascend or Stitch Data. These are like pure data integration things, decodable for the stream processing. We kind of have that overlap with quite a few, mainly because we aim to be sort of more of an end-to-end platform. And so the idea is you can come to the Meroxa platform, write code in your favorite language, write a stream processing application or write a pipeline, and we kind of handle the rest of it end-to-end. Whereas a lot of the competitors are very focused on a specific thing. So, lots of people that do data things like Python. So you can write your stream processing application in Python. You can import Python libraries that you wrote or your organization has, load them up and actually deploy them on our platform, and we'll run them and use those to process your data. And so, yeah, that's the core difference, I think, is really also, if you look at the team's background, we're all very developer tools focused. And so really that's the approach that we're taking, the whole idea of shift left towards the engineers. It's really empower software engineers to do data engineering type things. And so, yeah, you don't have to be an expert in Kafka and understand, streaming paradigms and processing windows and delivery semantics and, figure out ordering. You can just write an application that feels like a very normal, Python application or JavaScript or whatever it is that you like to write. And you can deploy that, and we'll kind of do the heavy lifting to get the data to your function, apply your function to it, and deliver it where you need it to go.
Cool. And so I'm taking a guess that when you talk about a code first platform, that's
exactly.
That's the idea, right?
Yeah, exactly.
Putting the code ahead of the infrastructure,
Yeah.
and all the pipes related to it.
Yeah, exactly. You define the pipeline, you define your logic, your transformation, all in the code. So like I said, if your favorite language is Python, that's what you define in. You actually define all the edges in the DAG. Everything is in Python. You deploy it like you would any other application. So you commit it to Git, you get your colleague to review it. It kind of goes through the whole workflow. Yeah.
Kind of back to my previous question, since you mentioned Python, how does that compare in that range between Go and the JVM?
Yeah,
for efficiency.
Python, yeah, for efficiency, Go is probably like magnitudes faster, magnitudes more efficient because it's a statically compiled language. But if you talk about developer velocity and richness of libraries, I think Python kind of wins hands down when it comes to data integration, data transformation, just because the tooling is so rich. And yeah, it's very, very approachable. So getting something up and running that does something powerful, solves your problem in Python is fairly trivial. To do the same in Go, it's a lot more work, a lot more code. It's a lot more verbose. So yeah, my main background, most of my experience, at least in the recent years, has been in Go. But yeah, quite like Python. Enjoy writing Python too. If there are no other questions, as my sort of parting request is, I'd love for people to check out Conduit, which is our open source tool. It's entirely free. You can just go to Conduit. I'll share the slides. I think if you're working with data, you want to grab data from somewhere, transform it. It'd be worth checking out.
Excellent. Yeah, we can put a link to that in the when this video gets posted to our YouTube channel.
Cool.
Okay. All right. So I'm just going to flip back to my screen. to wrap us up on the presentation piece. All right, so this is our last Space Data Hackers for the year because we've got we're last Thursday of the month, and guess what comes at the last Thursdays of November and December. It's not exactly the holidays, but we do want to make sure that we give people time to spend doing those wonderful things. So we will reconvene January 25th. We'll have a space cybersecurity talk. Yes, finally, Space Data Hackers will actually be talking about hacking. I can't tell you how many times when I tell people, oh, Space Data Hackers, it's like, oh, you guys are hacking satellites? No, we're not. But we're going to be talking about it when we next come together in January. So really looking forward to that. Okay. So right now I will stop and thank everyone for attending our session tonight, and Lily for presenting. This is really cool stuff, and hope you all get a chance to try out Conduit, and we'll see you next time. I'm gonna stop the recording now.